In this lecture, we'll be going through first introducing the pH scale, which many of you probably are familiar with from high school chemistry. And then we will go on to the Bronsted-Lowry definition of acids and bases. We talked about the Arrhenius definition before, but in the Bronsted-Lowry definition, you define an acid and a base depending on whether they donate a proton or receive a proton. So an acid would be a chemical that has a free proton that it can donate to another compound, right? And that compound would be considered a Bronsted-Lowry base, one that can accept that proton. Right? And one of the things that happens after this takes place, the acid, the compound that gave up that proton, will have, when that proton is missing from it, right, it gives up a positive charge with the proton, it becomes negatively charged, and we call that a conjugate base. So we have an acid and a conjugate base. And the base, after it accepts a proton, becomes its conjugate acid. So a base will turn into a conjugate acid. Okay, so there's this relationship between acids and bases in the Bronsted-Lowry definition. Right, so this is from chapter 18, sections 2 through 4. It will briefly touch on section 4 at the end of the lecture. Right, so this is where we left off last time, talking about the autoionization of water, how one water molecule can take a proton from another water molecule, and then you have H3O plus and OH minus, which would be H3O plus would be the conjugate acid, OH minus would be its conjugate base. Right? And we saw how we could, take our equilibrium expression and write it in terms of this reaction, the autoionization of water. And we also mentioned that the H2O concentrations we can think of as constant. So then it reduces down to what we call the Kw, which is equal to the hydronium ion concentration, or H plus concentration, times the OH minus concentration, equals 1 times 10 to the minus 14th. This is where we're going to get pH from. Okay. In the absence of other acids or bases, again, these two concentrations would equal each other, and they would be 1 times 10 to the minus 7th. Okay. A change in the acid concentration, or the hydronium ion concentration, causes an inverse change in the OH minus concentration, and that's based on this equation. So if this one goes up, this one has to go down, and vice versa, because they have to always, the product of them has to be 1 times 10 to the minus 14. So the higher your hydronium ion concentration, the lower your OH minus, and conversely, the higher the OH minus, the lower your hydronium ion concentration. So you can define terms acid and base, or acidic and basic, in terms of the relative concentration of each of these. So in an acidic solution, the hydronium ion concentration is greater than the OH minus. In a basic solution, the OH minus concentration is greater than the hydronium ion concentration. And when they're neutral, you have equal concentrations of both. So if we wanted to get calculate between these concentrations, right, we'd have to use the Kw, divide into the Kw. And remember, Kw equals 1 times 10 to the minus 14. Okay, so you can easily convert between the two concentrations. And again, when this one's bigger, it's acidic. When this one's bigger, it's basic. And only when they equal are they neutral. So let's try, before we get into pH, the details of that, let's try some practice questions. Calculating H3O minus concentration or OH minus concentrations. So a research chemist adds a measured amount of HCl gas to pure water at 25 degrees Celsius. They obtain a solution with a hydronium ion concentration of 3 times 10 to the minus 4 molar. Calculate OH minus concentration. Is the solution neutral, acidic, or basic? Okay, so we could, answer that last one probably just without really doing anything, right? Without actually solving this. HCl, remember that is a strong acid. So if that's in being added to water, right, that's like adding an acid to water, so this solution is going to be acidic. Okay? But we can prove that based on the concentrations of hydronium ion and OH minus here. Right, so how would we do that? Well, you need to set this up for Kw, right? Kw equals 1 times 10 to the minus 14th, and that equals the hydronium ion concentration multiplied by OH minus concentration. So this is what we're going to use. We rearrange this to solve for OH minus, and so that's Kw divided by hydronium ion. When you do that, we get 3.3 times 10 to the minus 11th molar. And sorry, there's a typo here. This should be 3 times 10 to the minus 4. So if you compare, if we go back, right, that was 3 times 10 to the minus 4 in this problem. So this is lower than this, right? Again, this is a typo. Don't pay attention to minus 14. It should be minus 4. Okay. And because H3O plus is greater, OH minus is smaller, this is an acidic solution. Okay, second practice question. Which of the following 3 solutions would have the highest pH? Okay, we have a solution of NaOH, a solution of H2SO4, and a solution of HCl. Right. So if we think back, we haven't talked about pH yet, but just a little ahead, right? The pH scale goes from 0 to 14, okay, with 0 to 7 being acidic, the acidic range, and 7 to 14 being the basic range. And if you're neutral, you'd be right at 7. Okay? So a higher pH means you're going to be more basic. So in these solutions, right, we have a strong acid HCl, a strong acid in sulfuric acid, and then we have a strong base. So the highest pH solution here would be A. That would be the base. It would give the highest pH. Okay, so that's a fairly easy question once you know the pH scale. Right. And the pH, how do we find pH? Well, pH, it's a measure of the hydronium ion concentration or proton concentration. Remember, those two terms are interchangeable. H plus, when it's in water, will make H3O plus, so we use these interchangeably. Right, so pH is just a measure of that, and it's a log scale to make it a little bit easier to deal with. If you were just using concentrations, like 1 times 10 to the minus 4 or 3 or 7, those are very small numbers, so they use this log scale to make it just easier numbers to work with. So pH, the equation for it, and this is an important equation, pH equals minus log of the H plus concentration. We can write another term that's very similar to this, but it's describing the OH minus concentration, and that's POH, and that's equal to minus log of the OH minus concentration. Okay. Right, so if we look on the scale here, starting at neutral 7 pH, right? Some of the more household items you'd run into, the pHs are listed. A very strong base, NaOH, would be a 14 pH at 1 molar. And going lower now, we go into the acids. Okay, and some of those are listed. And a very strong acid, 1 molar HCl, would have a pH of 0. And remember, these are related by kW. So kW is 1 times 10 to the minus 14th, and it equals those two concentrations multiplied by each other. So if we do the log form of kW, we take negative log of kW would be negative log of both of these. And we know kW is 1 times 10 to the minus 14th, so the negative log of that would be 14. And the negative log of both of these we've defined up here as pH and pOH. So the pH plus the pOH has to equal 14. So that's another thing that's very important to remember. So let's try a practice question. Calculate the pH for a 0.05 molar HCl solution. Right, we have our equation, pH equals minus log of the H plus, and we also know HCl, when it's in solution, is going to fully dissociate and form H plus ions, which then, of course, will make H3O plus in water, but let's just keep it simple and abbreviated as H plus. So if we have 0.05 molar HCl, we really have 0.05 molar H plus ions. So we can just simply plug that into our equation for pH. So negative log of 0.05, and we get 1.3. So that would be the pH of a 0.05 molar solution of HCl. We can also discuss the equilibria in terms of bases. And you can use this Kw expression to help with that. So we've discussed the weak acid equilibrium. A weak base equilibria would be shown here. So we have ammonia plus H2O goes to NH4 plus OH minus. And then if we wrote our equilibrium expression to this, what we would get here is, if we did this for a weak acid, we'd get a Ka value, but since this is a base, we call this Kb. Okay, so you get the products, which would be the conjugate acid plus OH minus, divided by the base. Okay. To calculate the pH here for a problem like this, you'd have to obtain this OH minus concentration at equilibrium, and then you'd use the Kw relationship to convert that back into either a H plus concentration, or you'd convert this to a pOH and then use the pOH and 14 to get the pH. Right, so what would this look like, right? If you have, it's very similar to our weak acid that we discussed in the last lecture. If you have a weak base, it will take a proton, this NH3 group will take a proton from OH, H2O, excuse me, and give you OH minus, and you produce ammonium NH4 plus. Okay, but this is an equilibrium, right? It's weak, so only a very small amount of it actually ionizes into ammonium. So you get a very small amount of the products being formed. Okay, so to calculate the pH, just in summary, of a basic solution, right? You have to obtain the OH minus concentration at equilibrium. Then you use the Kw expression, right, where Kw equals hydronium ion or H plus times OH minus. So then you'd solve for your H plus concentration, or you would just take that concentration of OH, get your pOH, and then you can work with the pKw, which is 14, right? 14 equals pOH plus pH. So doing it that way, both ways are equivalent. You're just, some people might think it's easier to work with this way, but you're doing the same steps, you're just doing them in a different order. Okay, so let's try a practice question using this principle. What are the H plus and OH minus concentrations in household ammonia, an aqueous solution that has a pH of 11.7? Okay, so we're given a pH. pH is 11.7. So we can use that equation. pH equals negative log of H plus. We can rearrange this. So that'd be negative pH equals log of H plus. Right, and then to get rid of the log, you would do 10 to the power of minus pH. And that would get rid of the log, and we'd be left with H plus. Okay? So, if you're good with math, right, you can just remember this equation. If you're not so good with, knowing what to do with logs, you might want to just kind of remember this equation as well. 10 to the negative pH equals the hydronium ion concentration. Right, so here we can plug in our value for pH. So H plus equals 10 to the negative 11.7. And that is 2 times 10 to the minus 12 molar. Okay, so that was easy. That's the easy part. The harder part becomes, once we have that, getting OH minus, because we're given a pH, right? That's directly related to H plus. Now to get OH, we're going to have to use our relationships, the KW or the pKw. So two ways to do this. Let's start the first way using KW. So KW equals H plus times OH minus. Right? And we know KW is always 1 times 10 to the minus 14th. We just calculated H plus, so if we solve for OH minus, we should just be able to plug things in, right? So it's KW divided by H plus. So that's 1 times 10 to the 14th, negative 14th, divided by 2 times 10 to the minus 12. So that would be 0.05 molar. Okay, so that was the first way, pretty simple. Let's try the second method, actually using the pH. So we're given a pH here of 11.7. Right, and remember the relationship pOH plus pH has to equal the pKw, which would just be 14. Right? KW is 1 times 10 to the negative 14, and if you take the negative log of that to get pKw, right, that would just be what the exponent is, the positive version of that, which would be 14. So now we can rearrange this. pOH would be 14 minus pH. So that's 14 minus 11.7. which would be 2.3. Have the POH. We know POH equals negative log of OH minus. Right, so if we take the raise 10 to the negative POH, we would get OH minus, which would be 10 to the minus 2.3, which would be 0.005 molar. Okay, and there's a typo there. Sorry, this up here for part 1 should have been 0.005 molar, right? Because these methods should give you the same answer. So, you know, on an exam, pick whichever way makes more sense to you, but they are equivalent. Okay. So Bronsted-Lowry is the second definition of acid-base that we will use in this class. And it's all about protons, okay? An acid is, a Bronsted-Lowry acid is anything that donates a proton. Right, so a proton donor is an acid. So an acid, therefore, must contain hydrogen in its formula. But not everything that has hydrogen in its formula will be an acid, okay? It has to be ionizable hydrogen or ionizable proton. It has to be able to be given up to be an acid. Okay, and base, conversely, is a proton acceptor. So anything that accepts an H plus ion. So a base must contain a lone pair of electrons to be able to capture that H plus. So in the Bronsted-Lowry definition, right, base has to have a lone pair of electrons. Right, so in this definition, an acid-base reaction is a proton transfer process. Remember in the Arrhenius definition, we defined an acid as something that increased the H3O plus concentration in water, and a base would be something that increased the OH minus concentration. And then an acid-base reaction would be an H plus reacting with an OH minus. Okay, that was the Arrhenius way of thinking. In the Bronsted-Lowry way of thinking, we're talking about proton transferring processes. And the Arrhenius definition works well for strong acids and strong bases, but this Bronsted-Lowry definition is better for weak acids and weak bases. Right, so here's an example. HCl, which would be a strong acid, and H2O, when you put that in water, H2O is acting like the base. Okay, HCl is going to be donating a proton, and it donates it to H2O to make H3O plus. Right. So here HCl is our acid, H2O is our base. Our conjugate base is Cl minus, right? What the acid becomes after the transfer. And H3O plus is our conjugate acid, right? That's what the base becomes after the transfer. If we look at something like a weak base here, NH3, NH3 has a lone pair on it. It's going to accept that proton from water. So now NH3 is our base, and H2O is acting like our acid. All right, and we've mentioned this before, kind of alluded to it, but here we kind of see the details of this, conjugate acid-base pairs. Okay, the forward reaction, let's try hydrogen sulfide plus NH3. Okay, hydrogen sulfide will be donating a proton and turning into HS minus. NH3 is going to be accepting that proton and turning into NH4 plus. Okay, so NH3 is our base, H2S is our acid. Okay, our conjugate base now
is HS minus, and our conjugate acid is NH4 plus. Okay. So and to see that, if you did this in the reverse direction, right, if you're looking at in this way, NH4 plus is what's going to be donating the proton to turn back into NH3, and HS minus is what's going to be accepting the proton. So the thing that is a acid in the forward direction is a base in the reverse direction, and vice versa. Okay. So H2S and HS minus are conjugate. We call this a conjugate acid-base pair. Likewise, NH3 and NH4 are also a conjugate acid-base pair. Okay. So a Bronsted-Lowry acid-base reaction occurs when an acid and a base react to form their conjugate base and conjugate acid respectively, right? And that's just shown here, right? Generically, your acid 1 turns into your conjugate base 1, base 2 turns into the conjugate acid 2. And here's a table of some conjugate acid-base pairs. Okay, so if you had the acid HF, the conjugate base is just going to be F minus. If you have something like carboxylic acid, HCOOH, that would be formic acid, right? That turns into HCOO minus, right? It gives up a proton, and they have a minus charge there. Right. Something like ammonia, this can act as an acid, right? It's going to give up a proton, but it starts with a plus charge. So when it loses the plus charge from the proton, it turns neutral. Okay. Usually your conjugate base will have a negative charge, but here's one example of a time when it would just be neutral because you're starting with that positive charge. Okay. And likewise, the base here, right? In the reactant part, when it turns into a product, it's just going to have a proton added to it, and then thus it's a conjugate acid. Okay, let's try a practice problem with this concept. Okay. The following reactions are important in environmental processes. Identify the conjugate acid-base pairs. Okay, so if we look at that first reaction, we have H2PO4 minus plus CO3 2 minus. Okay, and so that, if you just look at the reactants, that might be hard to tell, okay, what is my acid, what is my base? I guess the H2PO4 minus is the only thing that has a hydrogen in it, so it has to be the acid, right? But these aren't necessarily acids and bases we're used to seeing. So looking at both sides to see which it actually accepts the proton and which gives it up is key. So you see that it goes from H2PO4 to HPO4. So we're losing a proton. Right, so by definition, this is our acid. In that direction, so change color here. That would mean CO3 2 minus is our base. Okay. And when H2O PO4 minus loses a proton, this will be the conjugate base. And likewise, when CO3 2 minus gains a proton, it forms its conjugate base. Conjugate acid. And the second reaction, we have H2O and SO3 2 minus. H2O in this one is going to act like our acid, and S3O2 minus will act like our base. Right, that means our conjugate acid would be our base with a proton added, so HSO3 minus would be our conjugate acid. So SO3 2 minus is our base. OH minus would be the conjugate base of H2O. Right, so it's sometimes helpful to draw tie lines. Right, so our acid would turn into our conjugate base, and our base turns into our conjugate acid. Right, so on this reaction, acid turns into the conjugate base, and base would turn into our conjugate acid. Right, so they're all related. How do we determine the net direction of a acid-base reaction? Right? Well, it depends on the relative strengths of the acids and bases involved. So a reaction is going to favor the formation of a weaker acid and base. So the reaction for in this case, how it's written, right? We have H2S, which would be a stronger acid when we're comparing it with the conjugate acid, right? On the other side, H2S is stronger. NH3 as a base is going to be a stronger base than our conjugate base, which would be HS minus. So in this case, the equilibrium is going to lie towards the products because those are weaker acid and weaker base being formed. And here's a list of the relative strengths of conjugate acid-base pairs. So the stronger the acid is, the weaker its conjugate base. We've mentioned this before. When an acid reacts with a base that is further down the list, the reaction proceeds to the right. Right. So if you have an acid, up here and a base that's further down here, that reaction is going to proceed towards products, right? Because your conjugate acid that the base forms is going to be weaker than the acid you started with, and the conjugate base that you form from your acid will be weaker than the base that you're starting with. Okay. So you'd be favoring the production of weaker acids and weaker bases. So if we try a practice problem using this principle, predict the net direction and whether Kc is greater or less than 1 for each of the following reactions. Okay, and you can assume that we have equal initial concentrations of these species. So now we need to identify which of these is stronger. So we have H2PO4 plus NH3 goes to HPO4 2 minus plus NH4 plus. So just in terms of base, NH3, let's look at the acid first, H2PO4 and NH4. So if we look back on this list, H2PO4 is here, and NH3 is here. Excuse me, NH4 is what I'm looking for. There we go. So H2PO4 is actually a stronger acid than our conjugate acid. So this is stronger, and this is weaker. Okay, now let's compare NH3 and HPO4 2 minus. NH3 is a stronger base than H2PO4 because base strength is increasing going down. So again, this is stronger and weaker. So reaction will proceed towards the right. So in this case, equilibrium constant for this is going to be greater than 1. Okay. Our second reaction, H2O plus HS minus. Is H2O a stronger stronger acid? It's acting like an acid in this. Or is H2S? Well, it turns out H2S is, if we look back here, H2S is here and H2O is down here, right? And so anytime you have that, that's weaker and this is stronger. The other conjugates are going to be the same pattern, so this would be a weaker base than OH minus. So what does that mean? We go from strong to weak, so the equilibrium will lie towards the left, so Kc would be smaller than 1. Okay. Another question kind of dealing with the same principle. Given that 0.1 molar of HX, which would be blue and green, so X is going to be green, has a pH of 2.88, and 0.1 molar HY, which is blue and orange, so Y is orange, has a pH of 3.52. Which scene best represents the final mixture after equal molar of solutions of HX and Y minus are mixed? So here, there's what they're saying there is our reaction is going to be HX plus Y. And what would we go to? We'd go to X minus plus YH, or HY. Okay. So how do we know which is a stronger acid? Well, we can look at the pH. So HX has a pH of 2.88 and HY has a pH of 3.52. So the stronger acid will have a lower pH. So HX will be stronger and HY will be weaker. Right, so we know the equilibrium is going to go to the right. So what does that mean? That means we're going to have, if we have equal amounts to start of HX, which would be blue and green, plus Y, which is just orange, we're going to have at equilibrium more of the blue-orange molecule and the green by itself. So if we look here and count these up, in case 1, let's see how much HX do we have, how much X minus, how much Y, HY, and how much Y minus. Let's just count these up for all choices. Okay, so HX would be blue and green. So 1, 2, 3 is what I'm counting. Blue, sorry, just green by itself, we'd have 3. HY would be blue and orange, so 1, 2. And then Y by itself would be just orange, so 1, 2, 3. Oh, sorry, there's 3 HYs and 3 Y minuses. Okay, so that's all equal molar concentrations of everything. So we know that's not going to be the case at equilibrium because, again, we're going to favor the production of products. So in choice 2, all of those numbers would be 4 for HX. X minus would be 1, 2. HY would be 1, 2. And Y minus is 1, 2, 3, 4. So in this case, you're favoring Y minus and HX. So that would be the reactant side. So, this is not the case either. So we know it must be 3, but we can, count these up to be sure. So blue and green, we have 1, 2. And X minus, we would have 1, 2, 3, 4. For HY, blue and orange, we'd have 1, 2, 3, 4. And for Y minus, we'd have 2. Right, so this is favoring X minus and HY. So this, and those are the products, right? So that would be our picture we'd have at equilibrium. And again, how we know that? We haven't done any equilibrium calculation. We just know that HX is a stronger acid because it has a lower pH. And this reaction favors strong acid and strong base going to weak acid and weak base. It favors that direction. Okay. So that's all well and good if you know relative strengths of acids and bases. Sometimes you don't really know that, though. And so you're going to have to solve these problems using the same principles we saw when we discussed chemical equilibrium. Okay. So the approach we use, first and foremost, usually the case in all the problems we do, you have to write a balanced chemical equation. Okay. And from that, then you can write an expression for Ka. Just like you wrote an expression for Kc when we're talking about equilibrium, in acid-base equilibrium, the expression is Ka. It's a little bit simpler. Okay. Then you define X as the change in concentration that occurs during the reaction, because you usually don't know that. You construct a reaction table, just like we've done before, an ICE table. You make assumptions that are going to simplify the calculation. You substitute the values into the expression for Ka, and then you solve for X. And then finally, you can check if the assumptions are justified. And really, usually in this class, they're going to be justified. Right. So just a quick note on notation. Molar concentrations are indicated by these square brackets. Okay, so that's a concentration, and it's going to be in terms of moles per liter. Right. Bracketed formula with no subscript indicates an equilibrium concentration. H3O plus concentration from autoionization of water is negligible. Remember, we talked about how water will just naturally dissociate a little bit into H3O plus and OH minus. But we can consider that, that just at neutral pH, that concentration is 1 × 10 to the -7th. Okay, so that's a very low concentration in relative terms. Okay, so we can just kind of negate that. You don't have to add that amount of H3O plus into whatever your weak acid has. We can just kind of ignore it. Okay. A weak acid has a small Ka value, and its dissociation is negligible. So we can assume that the HA acid, weak acid concentration that's at equilibrium, we can assume that doesn't really change very much and just use the initial concentration that we're given. So again, you don't have to subtract how much of your conjugate base you are making from that acid. This will make more sense when we go through a problem. But you don't have to subtract that amount because we're assuming that usually the amount of conjugate base that's forming is going to be much, much less than the concentration of the acid that you started with. Right? If we included that in there, that'd be another variable, and it would be the same variable, X, and we'd have to put, this concentration minus X, and then the math gets more challenging. Okay, so let's go through a practice problem using acid-base equilibria, just to get kind of an idea here. Okay, so the problem we have phenylacetic acid, which given by this formula, none of that is very important except this part, right? Because that's what we know is the organic acid. We can simplify it as HPAC, right? So the PA, capital PA part, PAC is phenylacetic acid, and the H just stands for the proton that you're losing, giving up. Okay. Well, this builds up in the blood of persons with phenylketonuria, an inherited disorder that, if untreated, causes mental retardation and death. A study of the acid shows that the pH of 0.12 molar HPAC solution is 2.62. What is the Ka of phenylacetic acid? Right. So this might seem kind of challenging at first. So let's go through this. Where do we start? Okay, well, remember, the first and foremost, we need to write a balanced chemical equation. So we have our phenylacetic acid shown here plus H2O, right? It's in solution. We know it's an acid, so it's going to donate a proton, and its conjugate base would be PAC minus. And H2O is going to act like our base and pick up that proton and become H3O minus. Okay, so there's our reaction. And it is balanced. This is a 1-to-1 reaction. One proton from the acid mixes with one H2O, so that is balanced. Okay. We're trying to find Ka. It's asking us for a Ka. So now that we have that equation, we can write the expression for Ka. So it's going to be our concentration of our conjugate base times the concentration of our conjugate acid, the products in the direction this is written, divided by our concentration of weak acid that we started with. Okay, and remember, the H2O is in such great excess that we can consider that the concentration is not changing, so we don't have to take it into account for the equilibrium or acid constant. Right, so now we can write our reaction table. So we have initial concentrations, the change in concentration, and our equilibrium value. So the only thing that we're told, right, is that we had a 0.12 molar solution of our acid. Okay, H2O doesn't matter, great excess, and we can assume that we're not starting with any of these. Okay, so then our change is just going to be X, so we're going to lose concentration of our acid because some of it is going to ionize, and when that happens, the same amount of our acid that ionizes, it produces the conjugate base and the conjugate acid when it does that. Okay, so those are both plus X's. Now we can do our equilibrium values. So this would be 0.12 minus X. That's what we'd normally write. And these would both be X. Okay, so what we would typically do for this, we would typically try to, if we're doing like a chemical equilibrium, right, we would say, okay, 0.12 minus, so this would be, our expression for Ka would be X times X over 0.12 minus X. And then we'd have to, solve the math from there, but, which, would be a little bit challenging because we don't know the Ka value. So if we think about it, we can find X based on the pH. Right, remember your H3O plus concentration is going to be equal to 10 to the negative pH value. and we're given our pH in the problem as 2.62. So that would be 10 to the negative 2.62, right? And when we do that, we find that that is 2.4 times 10 to the minus 3 molar. So that's what X equals. Right, now we can plug X into our expression for Ka. So let's just include the X in the term for our original weak acid. So we'd have 2.4 times 10 to the minus third squared on top, divided by 0.12 minus 2.4 times 10 to the minus 3. Right, so if we did that, we would get that would be 4.89 times 10 to the minus 5. But now let's see if we can use a simplifying assumption, right? And remember, our simplifying assumption was we would ignore that change in our weak acid and just assume that at equilibrium it's very close to what we started with, right? So we'd put in 0.12 for that. So then our Ka value would be same expression on top, 2.4 times 10 to the minus 3 squared, right? Because that's what our x's are, value for our x, divided by now just 0.12. So now we're getting 4.8 times 10 to the minus 5. And if you actually compared these values, you would see that it's only about 2% off between the two. So this simplifying assumption really holds well. That's an acceptable amount of error, right? So we'll pick up here next lecture and work through more equilibrium problems with acid-base chemistry.